73% of companies running AI workloads on Kubernetes can't detect when their models are being poisoned, and traditional monitoring is completely blind to it.
Wait, are you saying our observability tools just don't work for AI workloads? So, we're covering why AI breaks traditional observability, the security gaps, and what AI-powered monitoring actually looks like.
By minute 4, you'll know exactly which blind spots to fix first. Let's get into it.
Welcome to the Platform Engineering Playbook Daily Podcast. Today's news and a deep dive to help you stay ahead in platform engineering.
Today, we're diving into why AI workloads are breaking traditional Kubernetes observability strategies.
Stick around to the end for today's headlines. Let's dive right in.
So let's talk about something that's been keeping platform engineering teams up at night. AI workloads are fundamentally breaking the observability strategies we've relied on for years in Kubernetes environments. And I mean really breaking them, not just making them a bit harder to use.
Breaking them how, exactly? Because I've been hearing rumblings about this from teams trying to deploy large language models and training jobs. But what's actually different about these workloads?
Think about it this way. Traditional Kubernetes observability was built for a world of microservices, short-lived containers, maybe running for minutes or hours at most, handling web requests, processing queues, that sort of thing. But AI workloads, we're talking about training jobs that run for days or even weeks, consuming massive amounts of GPU resources in ways our monitoring tools just weren't designed to handle.
Oh man, I can already see where this is going. The resource consumption patterns must be completely different.
Completely different is an understatement. I was talking to a platform team at a fintech company last week. They deployed their first major AI training workload, and their entire observability stack basically went blind. Their Prometheus metrics were getting overwhelmed, Grafana dashboards were showing nonsense because the scale was so different, and don't even get me started on the cost visibility issues.
Wait, how bad were the cost issues?
They burned through their quarterly cloud budget in 3 weeks because they had no visibility into GPU utilization patterns. Traditional CPU and memory metrics don't tell you anything useful when a single A100 GPU is costing you $40 an hour and your model is using 8 of them inefficiently.
This is exactly what I've been worried about. We've been considering deploying some computer vision models, but the observability question keeps coming up in planning meetings.
And it should, because here's the thing. It's not just about resource consumption. The security implications are massive, too. These long-running AI processes create attack surfaces that traditional security monitoring completely misses. Imagine a model training job that's been compromised and is slowly exfiltrating your training data over days. Your normal anomaly detection won't catch it because the baseline behavior is already so different from your typical workloads.
So, what specific observability gaps are teams discovering? Like, where do the traditional tools fall down first?
The first place is usually metrics cardinality explosion. AI workloads generate orders of magnitude more metrics than traditional apps. Think about tracking performance across different model layers, batch sizes, learning rates. One team told me their Prometheus instance started dropping metrics because they hit cardinality limits they didn't even know existed.
That's terrifying. You're basically flying blind at that point.
Coming up, we'll dig into exactly how teams are adapting their strategies and what new approaches are emerging to handle these AI-specific challenges, because there are solutions, but they require fundamentally rethinking how we approach Kubernetes observability.
So, walk me through what actually happens when you deploy something like a large language model training job into a Kubernetes cluster with traditional observability.
All right, let's get specific. Say you're deploying a model training job that needs 8 V100 GPUs, running distributed across multiple nodes. First problem, GPU metrics. Traditional Kubernetes monitoring with Prometheus and Node Exporter gives you CPU, memory, disk, network, but GPU utilization, GPU memory, tensor core usage, you're getting nothing by default.
And I'm guessing the NVIDIA GPU operator helps, but doesn't solve everything.
Exactly. Even with the GPU operator and DCGM exporter, you're only getting basic GPU metrics. But here's where it gets really interesting. AI workloads have this bursty pattern that's completely different from web services. During forward passes, you might see 95% GPU utilization. During backward propagation, it drops to 60%. During checkpoint saves, it plummets to near zero while maxing out network and disk I/O.
So your auto-scaling policies would go high-wire.
Completely haywire. I know a team that had their horizontal pod autoscaler spinning up new training pods every time the model was saving checkpoints because CPU usage would spike while GPU usage dropped. They were basically launching redundant $30,000 per day training jobs because their observability couldn't distinguish between different phases of the training cycle.
30,000 per day? That seems high.
8 A100s at $40 per hour each, running 24 hours, that's $7,600 per day per job. They had 4 redundant jobs spinning up. The math gets scary fast. And here's the kicker. Their cost allocation tools couldn't properly attribute GPU costs to specific teams or projects because Kubernetes labels don't propagate to cloud provider billing in a way that captures GPU usage.
What about the debugging challenges? When something goes wrong with an AI workload, how different is that from debugging a web service crashed?
Night and day different. When a web service crashes, you look at logs, maybe a stack trace, check your recent deploys. When an AI training job fails after running for 72 hours, you need to understand, was it a gradient explosion, a data pipeline issue? Did one of your distributed workers lose network connectivity during a critical synchronization phase? Traditional logging doesn't capture any of this.
Oh, and I bet the distributed nature makes it even worse.
Absolutely. Modern AI training is almost always distributed. Data parallelism, model parallelism, pipeline parallelism. You've got parameter servers, gradient aggregation, checkpoint coordination. One company I worked with had a training job that would mysteriously slow down after exactly 47 hours. Turns out their observability couldn't track cross-node GPU communication patterns, and they were hitting an NCCL timeout issue that only manifested when certain gradient synchronization patterns aligned.
How did they even figure that out without proper observability?
23 days of debugging. They literally had engineers taking shifts to watch the cluster. They ended up building custom instrumentation just to track GPU to GPU communication patterns. This is what I mean when I say traditional observability is broken for AI workloads.
And I'm assuming the security monitoring gaps are just as bad.
Worse, actually. AI models are intellectual property worth millions. Traditional security monitoring looks for unusual network patterns, privilege escalations, file access anomalies. But AI-specific attacks, model extraction through careful API queries, training data poisoning through subtle gradient manipulations, backdoor triggers being inserted during fine-tuning, your SIEM has no idea what any of this looks like.
Are teams actually seeing these attacks in the wild?
More than you'd think. I know of 2 cases in the last 6 months where companies discovered someone had been extracting their models through carefully crafted inference requests. The attacks ran for weeks because the request patterns looked like normal model usage to their security tools. The only reason they caught it was the cloud bill. Someone noticed inference costs were 3 times higher than expected.
This is painting a pretty grim picture. Stick around, though. We need to talk about what teams are actually doing to solve these problems, because I'm hoping there's light at the end of this tunnel. All right, so given all these challenges, what are teams actually doing? Because they can't just throw their hands up and say observability is impossible for AI workloads.
You're right, and the good news is that smart teams are developing new strategies, but it requires a fundamental shift in thinking. The first thing successful teams do is separate AI workload observability from traditional application monitoring. They're building dedicated stacks specifically for AI workloads.
Separate stacks, that sounds like it could lead to even more fragmentation.
It can, but here's why it works. AI workloads need different metrics, different retention periods, different aggregation strategies. For example, one platform team I know created a dedicated metrics pipeline just for AI workloads. They used Vector to collect GPU metrics, training metrics, and model performance data, then route it to a time series database optimized for high cardinality data like QuestDB or TimescaleDB, instead of trying to shove everything into Prometheus.
That makes sense. Different tools for different jobs. What about the real-time monitoring aspect?
This is where it gets interesting. Teams are building what I call AI-aware observability layers. Instead of generic dashboards showing CPU and memory, they're creating training-specific views. Progress through epochs, loss curves, gradient norms, learning rate schedules, all correlated with infrastructure metrics. When a training job slows down, you can immediately see if it's a GPU throttling issue, a data loading bottleneck, or an actual model convergence problem.
How are they handling the cost visibility problem?
Three main approaches I'm seeing. First, custom resource labeling schemes that capture not just who's running the job, but what model, what data set, what experiment. Second, integration with cloud cost APIs to pull real-time GPU pricing. Third, and this is clever, they're building cost prediction models. Before you launch a training job, the system estimates the total cost based on your model size, data set, and historical training patterns.
That's proactive rather than reactive. I like it. What about the security monitoring gaps?
This is still evolving, but the leading teams are implementing what they call model-aware security monitoring. They're tracking things like inference patterns to detect extraction attempts, monitoring gradient updates for signs of poisoning attacks, and building behavioral baselines for each model. If your language model suddenly starts getting queries that are statistically different from its training distribution, that triggers an alert.
So they're basically building domain-specific security tools for AI.
Exactly. And here's a concrete example. One team built a system that fingerprints every model they train. It tracks the model architecture, training data hash, hyperparameters, and performance benchmarks. If anyone tries to exfiltrate the model, even if they manage to copy the weights, the system can detect when that model is being used elsewhere based on its inference patterns.
That's sophisticated. What tools should teams be looking at if they want to start improving their AI observability today?
Start with the basics. Get the NVIDIA GPU operator deployed if you haven't already. Look at tools like weights and biases or MLflow for experiment tracking. They integrate well with Kubernetes. For metrics, consider dedicated solutions like Determined AI or Run.ai that understand AI workloads natively, and critically, invest in log aggregation that can handle the volume. AI workloads generate massive amounts of logs, and you need something like Loki or Elasticsearch with proper retention policies.
How about teams that can't afford a complete overhaul?
Start small. Pick your most expensive AI workload and instrument it properly. Add custom metrics for training progress, implement basic cost tracking, set up alerts for common failure patterns. Use this as a proof of concept to show the value, then expand. The key is to not try to force AI workloads into your existing observability patterns. Acknowledge they're different and build accordingly.
Any predictions for where this is headed?
I think we're going to see AI-native observability platforms emerge as a distinct category. Just like we have APM for applications and NPM for networks, we'll have AIM, AI model monitoring, as its own discipline. The platforms that win will be the ones that understand both the infrastructure layer and the model layer, providing unified visibility across both.
That makes total sense. The complexity isn't going away, so our tools need to evolve.
Here's my closing thought. The teams that master AI observability now will have a massive competitive advantage. As AI becomes more central to business operations, the ability to run these workloads efficiently, securely, and reliably will separate the winners from the losers. Don't wait for perfect tools. Start building your AI observability muscle today, even if it's with duct tape and custom scripts. The learning you gain will be invaluable as the tooling ecosystem matures. Before we wrap up, let's catch up on this week's infrastructure news. There's a critical security situation developing with AWS's new managed open clause service on Lightsail. According to InfoQ, they've launched this AI agent deployment platform, but it's shipping with some serious vulnerabilities.
How serious are we talking here?
We're looking at a one-click remote code execution vulnerability, CVE 2026-25253, that's already affecting over 17,500 instances. That's a massive attack surface for something that just launched.
Yikes. AWS pushing out a managed service with known critical vulnerabilities feels like a major misstep. Platform teams are going to need to weigh the convenience against the risk here.
Speaking of security, Cursor has taken an interesting approach to a problem we all face. They've built and open-sourced an entire fleet of AI-powered security agents.
What kind of capabilities are we talking about?
The news stack reports these agents handle everything from automated code review to vulnerability hunting, dependency patching, and compliance monitoring. They're leveraging Cursor's AI infrastructure to basically create an automated security team.
That could be a game changer for smaller platform teams who can't afford dedicated security engineers. Open sourcing it is a smart move, too.
For those diving deep into LLM architectures, Sebastian Rashka has published a comprehensive gallery comparing models like Llama 3, GPT-4, and others. It's focusing on the technical details, scale, decoder types, attention mechanisms.
This sounds like essential reading for platform engineers building AI infrastructure. Understanding these architectural differences is crucial when you're deciding which models to support.
Moving to container registries, the CNCF blog has a detailed guide on configuring registry mirror authentication using Kubernetes secrets, specifically for OpenShift environments.
Registry authentication is one of those things that seems simple until you're dealing with it at scale. Having a solid pattern for this with CRIO is really valuable.
They cover both manual configuration and automated approaches, which is great for teams at different maturity levels.
And finally, KubeCon Europe 2026 is introducing Open Sovereign Cloud Day as a co-located event. This is all about making digital sovereignty a practical engineering priority.
The CNCF announcement emphasizes they're providing clear definitions and shared language around sovereignty, something the industry desperately needs as more organizations grapple with data residency and control requirements.
It's about time we had a dedicated forum for this. Sovereignty isn't just a compliance checkbox anymore. It's becoming a core platform requirement.
That wraps up today's news. That's our show for today.
If you found this valuable, please subscribe and share with a friend who'd appreciate it.
Drop us a comment with your thoughts on today's topic.
Links to everything we discussed are in the show notes.
And check out platformengineeringplaybook.com for more resources and guides. Until next time.